All right, hello grade 10s. This is Euclidean geometry, and I'm going to take you back to some few theorems that you learned in grade 9, like congruency in triangles. So we are going to learn congruency, then we're going to remind each other congruency in triangles. That when we talk about congruency in triangles, we are looking for four conditions. The first one is side, 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 which means if all corresponding sides are equal, then therefore those two triangles are congruent to each other. So we have side, angle, side. So if we have that is a congruent triangle. Those triangles are congruent, angle, angle, side, and also right angle, hypotenuse, side. So these are the conditions that are going to help you the most when you are dealing with the what you call the parallelogram, or proving whether the diagonals of a parallelogram are equal, or no, not necessarily equal, but they bisect each other, or to prove that the opposite sides of a parallelogram are equal. So this congruency theorem does the most when it comes to those kind of proofs. Then also trying to remind you about the theorems around a parallelogram. That theorem number 1, we just need to adopt that opposite sides and angles of a parallelogram are equal to each other. So if we have this parallelogram number 1, it meets all these properties, then it has to be a parallelogram. Or parallelogram number 2, if the two pairs of opposite angles are equal, then that parallelogram, that quadrilateral, has to be a parallelogram. That was theorem number 1. Then theorem number 2 says the diagonals of a parallelogram bisect each other. So if there is a quadrilateral that is given, and you can see that the diagonals bisect each other, then that means that quadrilateral is actually a parallelogram. So that's just that. So you can see that over here, that this line has to be equal to this line, and this one has to be equal to that one in order for this to be a parallelogram. So that's just the theorem number 2. Then let's get into number 3. Number 3, it says if one pair of opposite sides of a quadrilateral are equal and parallel, then that's a parallelogram. That is a parallelogram. So we can just have this parallelogram over here, right? Yeah, not it's not what I was trying to draw, but basically you can get the idea what this is. All right, so this is what I was trying to draw. So this is the parallelogram. If this side is found parallel to this one and also equal, then this is going to be a parallelogram, right? So we have these three theorems around parallelogram, and you can see, we know most that each and every theorem has to have a converse of it. So which means if the diagonals bisect each other, then that is the parallelogram, or the diagonals of a parallelogram, they bisect each other. So it's just the theorem together with its inverse in everything. So let's just come to do some practicals in terms of answering some few questions to get together. Now in question number 1, it says in a parallelogram, in a diagram here, we have PQ. This is PQ, which is equal to QT. So PQ is equal to QT. So this line is equal to that line. So we have that information over there. And QR is also parallel to what? To TV. So QR is actually parallel to TV. So this is a parallel. Then RS is parallel to VW. So RS is parallel to VW, as you can see over there. So they are what? They are asking us to prove that PS is actually equal to WS. But before that, I would like to first give you some just what you call, it's one theorem about a midpoint. So let's just get into midpoint theorem just a little bit, right? So let's have this one. We are having triangle ABC, and it is found that we have this point D and point E over there, that this D is found to be in the middle of AB, so that makes D to be the midpoint of that. And this DE is joined this way. So should it be joined this way and found it bisecting this third side? This is the midpoint theorem. It says, what does it say? It says if a line drawn from the midpoint of two sides of a triangle, which means these two sides is this side AB and this side AC. So if this line is drawn from the midpoint of two sides of a triangle, that line has to be parallel to the third side, right? So we have that. So this line is going to automatically be parallel to the third side because it is drawn from the midpoint of two sides of a triangle, right? So yeah, let me just not write the theorem at large, but the idea is that a line drawn from the midpoint of two sides of a triangle, that line is what is going to be parallel to the third side and also have the third side. Let's not forget that it also have the third side. So if the third side is 2x, then DE is going to be x. If the third side is 10, then DE is going to be just 5. So we just have that information. And this theorem does have its converse that is very useful. So if I draw this and I make this information over here, say this is FGH, and we're having I over in the right in the middle of FG, and we have the line parallel to FG over there. We do have this point. This I is said to be in the middle of FG, so that means Fi is equal to IG, and this IJ is parallel to the third side, right? So we can see that we have this information over here, but we don't have this information that J is also in the midpoint of FH. But now this is gonna be the converse of the theorem that says a line drawn from the midpoint of one side of a triangle parallel to the second side, it is going to be bisecting the third side. So which means this side is also being bisected, but it is just not shown. And if it is not shown, then therefore that is not the midpoint theorem. It is actually the converse of the midpoint theorem. So should you say Fj is equal to JH, the reason for this statement is converse of midpoint theorem. So we have that. So this one is going to be automatically be equal to each other, but it's not going to be shown. Should it be shown, then therefore it's going to be the midpoint theorem. But if it is not shown, then it's converse of midpoint theorem. So the converse of midpoint theorem, how do you notice or how do you distinguish it from the theorem itself, is that you'll be having parallel lines and one line that is being bisected. Otherwise, in this one, you will be having you will be having 2 points that are in the middle of 2 sides in the triangle. You won't be having the parallel lines. You are going to have parallel lines as a conclusion, because of course there has to be parallel lines there, that because of the theorem that it says if a line drawn from the midpoint of 2 sides of a triangle, then it is going to be parallel and half the third side. So that is why now this parallel just comes spontaneously. So let's just get this for now and actually then continue to answer the questions that follows. Now what I have this very first question. The first question says, yeah, I like the fact that it does involve the very last current theorem that we spoke about. PQ is equal to QT. So PQ is equal to QT. Let me just use the different column. And QR is parallel to VT. So these lines are parallel to each other, and also these lines are also parallel to each other. So we have this information, we have some parallel lines, we also have Q that is in the midpoint of PT. Now with an understanding, we can say let me just change this one. We can just say PR is actually equal to RV. Then the reason is the converse of midpoint theorem. Okay, so which means we figured out that this line is equal to this line. But this pattern can continue because we also have this QR equal to VR, and you can see that RS is actually parallel to VW. So still we can say PS is equal to SW, because we are proving that PS is equal to W, and we can see that this line, not necessarily using this one, we can just say use 2 here and using 3 here. So these lines are going to be equal to each other because we also have a converse, because we have this R, which is the midpoint of this one side, and RS is parallel to the second side. Then we know that this RS is going to bisect the third side as well, and the reason is converse of midpoint theorem. Okay, so we have that. I think we are done with answering number 1. Let's come to number 2. Number 2, we have this information over here in the diagram. AB is parallel to DC, and AD is parallel to CB, and AE is equal to FC. So AE is actually equal to FC. So what do we then do? We know that AD is actually equal to BC, and the reason these are the opposite sides of a parallelogram. Okay, now after having that, we know that AE is actually equal to FC, and that one is given. Okay, so we can see that we are having, we want now, because we can see that the theorem that we to use is actually to notice that this line is also equal to that line. Should these lines are equal to each other, then therefore it is going to be a nice thing to say theorem 3 does apply, because theorem number 3 says if one line, because the idea we are proving that EBFD is a parallelogram. EBFD is a parallelogram. Since this line FED is already parallel to FB, then therefore we just need to find this last information that they are also equal, right? Should that happens, then therefore that is going to be a parallelogram. But we know that DE is equal to AD minus AE. Okay, minus AE. Actually, this one is equal to the whole of this line minus this portion, right? So that you go to DE. Also, BF is equal to BC minus, we said FC is equal to AE, so I can just say A minus AE because I'm still minusing the very same thing, right? Because BF, this one is equal to the whole of this thing minus this portion, so that's going to check BF. So we can see that if we have DE equal to AD minus EF and BF is equal to BC minus the very same thing, we can just say, all right, if that is the case, DE is going to be equal to BF. So DE is now equal to what? Equal to BF. Because, yeah, so it's equal to DE is equal to BF, right? So we basically have that. Now, after that, we can just say, therefore, EBFD is a parallelogram. And the reason for that is that one pair of opposite sides are equal and parallel, right? So if this line is parallel to this one and is also equal to this line, so theorem number 3 of proving a parallelogram does exist on this question. Then we are done. Then coming to the next one, yeah, in the diagram, PS is parallel to QR and QR is parallel to SR. So we have on this information 3 pairs of opposite sides that are parallel to each other. So let's prove that PXRY is actually a parallelogram. So PX, let me just say PXRY. So this is what we have. So we have a nice constructed diagram here, which is a parallelogram that makes this side being opposite to that one and that one is opposite to that one. But anyway, we just have that information. Now it is wise that we find this side equal to that side. Should that happen, then that is going to be a parallelogram. Now I'm thinking of finding out the relationship between some triangles, whether they could be congruent to each other. In triangle, let me just say, if I can test this one and that one and check if they can be congruent to each other, so that should they be congruent, then this line is going to then be equal to this one, right? Should that happen. Now the idea is to, after having removed all this, we just need to prove that PY is equal to XR. Should these lines that are opposite to each other be equal, can't be parallel, then therefore that is going to be a parallelogram. So which means in triangle PYQ and triangle SRX. So what is it that we notice here? We notice that angle PQS, which is this one, is equal to angle XSR. and this is the angle XSR, that is that angle. Now the reason is these are alternate angles. Okay, these are alternate angles, are equal because PQ is parallel to SR. Okay, now what else that we have? It's PQ. PQ is equal to SR, which is this side is equal to that side. Okay, and the reason these are the opposite angles of a parallelogram. Okay, now how about these ones? How about this? Let me just change color like thing. Let me just change the color. What about this Z over here that is not clear? This one is equal to that one. These are actually alternate angles. Okay, now that means y x is actually equal to q x r. The reason these are alternate angles are equal because y is a parallel to xr. Okay, then I think if these angles are equal to each other, and I think they will need the very same angles over here because these are the angles of on a straight line. So that means therefore OPYQ, which is this angle, is going to be equal to angle SXR, and the reason for this is because these are the angles on a straight line. So if this, for example, if this could be 100, this one and this one is also 100, then this one has to be 80 so that it maintains the straight line, and this one has to be 80 so that it maintains the straight line. So that is why if these angles are equal to each other, then these ones have to also be equal to each other. So these are the angles on a straight line. Right, so we can now say triangle PYQ is congruent to triangle SRX. The reason for this, we have found that this angle is equal to that angle, and this angle is equal to this angle, and the side is equal to that side. So this is angle side. So we did prove that they are congruent triangles over here. So if that is the case, therefore P is then going to be equal to PY is going to be equal to XR. Reason it's from congruent triangles. So that means this angle, this side is going to be equal to this side in these congruent triangles. So we're done. Then therefore PXRY is actually a parallelogram. Reason opposite sides. Remember, this is and these are opposite sides. If you can construct this, you can see this quadrilateral they are talking about, this parallelogram they are talking about, that since PY and this line they are parallel already, and now we also found them equal due to congruent triangles. So we can say this is a parallelogram because one pair of opposite sides are equal and parallel. So that's what makes it to be a parallelogram. Then we are done with that one. How about the next one? The next one says, in the diagram, PS is equal to SQ. PS is equal to SQ. PS is equal to SQ. So we have that. Then SV is parallel to RQ. SV is parallel to RQ. Then PQ is parallel to VR. Then PQ, P what? PQ is actually parallel to VR. So we have that. So the first question says, prove that PVRS is a parallelogram. PVRS is a parallelogram. So I think we need to view all the theorems around the parallelogram now. Should it be the diagonals bisecting each other? That I think it's going to work with us, because I can see that PVRS is, we are having these diagonals over there. The one that I drew, these are diagonals. So if this diagonal, this line could be equal to that, and this one dealing on a naily, then this could be a parallelogram. So, but it is very clear that PT is equal to TR. Reason it's a converse, because you can see that this S is the midpoint, and we said the line drawn from the midpoint of one side of a triangle parallel to the second side, it has to bisect the third side, right? So that's the reason why now we say PT has to be equal to TR. So we say this is the converse of midpoint theorem. Okay, so that means we have already identified that these two things are equal to each other, right? Now, if this is a if that is happening, we are also told that this is actually what? But even if we cannot use these, I think the opposite sides may be very useful here, because we know that I'm sorry to wrap this up. The idea is to say, since VR equal to SQ, raising these are the opposite sides of a parallelogram, right? So if that's the case, VR is also equal to SP, and they are both equal to SQ, right? So we have that. Then we can see that quadrilateral that we can construct here, you don't necessarily have to construct, but to do that it's only about viewing, this is actually a parallelogram. So this is basically what we have. So therefore PVRS is a parallelogram. The reason being, this side is equal to that side, and they are already parallel to each other. So one pair of opposite sides is equal and parallel. So you can see that theorem number 3 is being used mostly in these questions that we have already done. Then what are we having? We say the parallelogram because one pair of opposite sides equal and parallel. See, then we are done with that one. Then number 21.2, PT is equal to TR. We need to prove that PT is actually equal to TR. That makes us to go back to that theorem, that converse theorem, because we have this S which is in the middle of QP, and this ST is actually parallel to this. then we can see the converse of midpoint theorem over here. That makes PT being equal to TR, and the reason this is the converse of a midpoint theorem. So it is really up. So let's check if we have another question. Yeah, that's a nice beautiful question. Let's get into this one. In the diagram, AD is equal to DB, AE is equal to EC, and DE is equal to EF. So we all have that. So prove that AFCD is a parallelogram. AFCD. I think this is the same as what we just did there. That this is a parallelogram because we can see that the diagonals, they bisect each other. So we can just say AFCD is a parallelogram. It is a parallelogram because diagonals that are bisecting each other. So we can see that since this diagonal is being bisected by E and this diagonal is bisected by E, remember that our quadrilateral, our parallelogram is going this way. So you can see that in the absence of this portion, we have a parallelogram over there. So by the way, we are done with that one. Coming to the second one, prove that DFCB is a parallelogram. So it is wise that we managed to actually know that DB is equal to FC. Then if that is the case, we can tell that oh yeah. So what we can do then, we can just say DFCB is a parallelogram. So we need to prove that DFCB is a parallelogram. We can either prove that DF is equal to BC, whereas we can also prove that something. All right, now the idea is the idea is to actually make it a point that okay, I think I'm gonna take the long way probably, but I think I need to introduce in triangle. I can say we are having triangle ADE and triangle F, okay, C FE. What is it that you notice in these triangles? Because I want to make there some relationship. So angle side, okay, side one side EA is equal to AC, and the reason is given, right? So we also have DE being equal to EF, and the reason for that it's given. And angle AED is equal to angle CEF, and the reason is vertical opposite angles, right? So we can now tell that this triangle ADE is actually congruent to triangle CFE. Raising, because this is side angle side, so this side equal to this one is equal to this one, and these angles are equal to each other. So that's what we have done. Therefore, what we can say, FC is equal to AD, and raising from congruent triangles. So we needed to find that this angle, this side is also equal to that side. So should those sides are equal to each other, which means we have these sides that are equal to each other. Okay, so that means FC is equal to BD now, right? Equal to BD, because they are both equal to AD, right? So also we can tell that angle A is equal to angle C. You can see that these angles are alternating to each other. Now Z. Okay, so these angles are alternating to each other. So should this happen, alternate angles are equal. Okay, this A is equal to C, not because they are alternate, not because they are alternate angles equal. It's because of congruent triangles, right? So but line AB is going to be parallel to CF, raising, because corresponding alternate angles are equal. So if this line now is parallel to that, and we've already proven that this is equal to that, then therefore DFCB is a parallelogram. So therefore DFCB is a parallelogram. So this is a parallelogram. Reason, it's one pair of opposite sides equal and parallel. So a lot that just happened. Probably there is a shortest way, but I couldn't find it. Now write down two things that can be deduced about DE and BC. DE and BC, let me just wrap that. DE and BC. If that is the case, DE, we can actually tell, or probably number two, I just found another way of doing the very same thing, that DE is actually half of BC, right? It's actually half of BC. Also DE, we know that it's parallel to BC, that's the midpoint theorem. That's the midpoint theorem. It's from the midpoint theorem, right? Then we can say that if that is the case, BC is just equal to 2DE, but 2DE is the same as BF, so BC is equal to BF, DF, df, because this is equal to that. So if you multiply de twice, it's the same as finding the whole df. So we can see that since de is parallel to that because of midpoint theorem, and also de times 2, which means de plus fe is equal to bc. So you can see that these sides are parallel and equal. So therefore, what this would dfcb, this is still 20.2, is a palm raising opposite one pair of opposite sides equal and parallel. So this is just another option if you don't opt for finding these other ones. That I find it easy for this one because I just squeezed this one. I knew that de is equal to half of this. That means if that is the case, this is how it is. Then write down two things that can be deduced about DE and BC. DE is actually, you can just repeat that. So those two things, DE is half of BC. So this is the first thing. And also DE is parallel to BC. So these are the things that can be deduced about DE and BC. So that's basically that for this theorem. So do we have any other question? I don't think so. So see you in the next question if there is any. Bye.